this Christmas tree lecture, where the general idea is to tell you about the coolest thing I learned about trees during the year. Trees are somehow, the center of computer science, and so there's generally much more to talk about in any particular year. But today, instead of talking about the coolest thing I learned this year, I'm going to talk about something I learned several years ago because it's just so beautiful, and I didn't get to talk about it at the time since I was in Sweden. So this is the 15th annual, except that I missed once or twice being out of the country. Now, before I warm up, though, I'm going to talk about Christmas because here's the time for giving, and I have some great gifts to recommend to the audience. So for example, one definite thing to ask for from your loved one. Okay, anyway, this book came out 15 years ago, and so you might say it's an old book, but it's new because it came out in paperback for the first time now. And not only that, but it's been totally, brought up to date because it actually talks about the internet in a modern way and things like that. So it's been and it doesn't have a single known mistake in it. Which means that, okay. Anyway, it's, I think they did a nice job putting it out in paperback, and it's got stuff about trees in it, that's why I mention it, spanning trees, and tree structures used all the way through. So it, in case somebody doesn't know what to give you, this is, hint, hint. Now, on the other hand, even better. Is this one, Generating All Trees. See that? Now this book actually inside of here contains almost everything that was in my previous Christmas tree lectures. I mean, there's lots of, there's all kinds of stuff in here. Look at all the trees here. You see all you're seeing trees. Anyway, there's beautiful pictures and. Lattices of trees, that was one of the subjects we talked about. Drawing beautiful trees. Okay, and even if you don't like trees, you can go on to the next section about the history of combinatorial generation, and it has wonderful pictures in there too. So now this one I looked on Amazon today, and it's selling for $16.99 plus shipping, I guess. And it's number 618,000 on their list, even though it's got 5-star rating. But not only that, you can if you look on Amazon and you don't want to buy from them and you want to buy from some place where some of the other places that they list, somebody is selling it for $140.85 plus $3.99 shipping. So just imagine if anybody. Once there must be a really spiffy copy. I don't know how they got for $140. Anyway, this is so there's all kinds of stuff about trees in here, and I have to give you one caution though. A year from now, I'm going to be holding up a hardback version, which costs a lot more than $16.99, which is going to have 5 times as much stuff in, or 6 times as much stuff as this, but including this. But I'm hoping somebody will read this, carefully in between, because there's an awful lot of fine print in here that has subtleties, and I want to get it right before it goes out in hardback. So so I want to know about that in the next 6 months or so. Now, one other thing before I finish this, in case you don't learn anything else this hour, I had to tell you something that you can use on your Christmas cards, and that is this. 2009, or I should have written this last, is equal to 1/2 plus 3 times 4 plus 5 times the quantity, 6 times 7 plus 8 times 9. Now, there's a fact that I bet you've never seen before. And so, and if you want to know how to get this, there's an exercise in here. You use trees to do it. And in fact, this is the only way to to insert signs in the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, including one division. You're allowed plus, minus, times, subtraction. Plus, minus, times, and divide. And this is the only way to put a division in there and still make it work. Okay, so there you are. Put it on your Christmas cards or whatever. Okay. Now for presents, I'm also giving away a whole bunch of stuff. For example, you see, 2009 is not only a year, but it's an awesome year because in Roman numerals, it's MMIX, and that's the number of my computer that I designed for the 21st for the third millennium, now if you want a book about MMIX, I have it here. Look at this. It's still shrink wrapped, and I have an extra copy. I'm giving it away. The guy from Boston gets first choice. All these other books I put up here, please take them away. I have spares of all this. I also have a book about MMIX, explaining it for Polish speakers. If you can't read Polish, maybe you like the Hungarian version. Okay. So now, there's also, however, let's see. So here's the. I'm going to put them out here so you can easily see. All right. So a bunch of other stuff here. You see, here's the one about trees that I showed you before. Except it's in Hungarian. Oh, no, wait. This is number 2. What do I want? This one. Yeah. This is the tree. No. Oh no. 4, 3, 4, 4. Aha. Trees. There we go. Okay. Yeah. So if you want to see the that same thing I showed you before, but in Hungarian, here it is for free. And then I got a bunch of other Hungarian and Polish and stuff here, and Japanese. Let's see. Yeah. The tree one isn't translated into Japanese. And then I got a whole book here, volume 1 of The Art of Computer Programming. And this is in Czech. So there you are. And I hope somebody who actually can speak the language picks them up. But otherwise, why not? You can always learn. All right, so now, today, spanning trees and aspects. This is such a beautiful subject. I can't resist, going into teaching mode and saying, here is one of the most fun things to teach that I know. It's something that to add to it to everybody's toolkit. The ideas are not. A lot of them don't need higher math, but higher math doesn't hurt for once you get started. And so I'm trying to get you started on this idea. A very beautiful subject of interest, I think, to anybody who ever has to work with graphs, and almost every application of computer to discrete things works with graphs. So I hope you enjoy learning about this if you don't already know it. Now, so the whole thing starts out with me getting my notes together, and it starts out with something that we call the matrix tree theorem. And the matrix tree theorem is I think it was my second or third Christmas tree lecture, years and years ago. very, very well-known important theorem, but I'm going to remind everybody about it and tell a little more. And it's a very simple idea. And I'm going to draw a simple directed graph. It applies to any directed graph, but I'm going to draw one that has 3 vertices, and I'm going to mention 6 arcs on it. There's 1, 2, 3, and so arc A goes from 1 to 2, arc B goes 2 to 3, arc C goes 3 to 1, and then I'm going to have arcs going the other way. I'm going to have going backwards. This is going to be capital A, and capital B, and capital C going this way. No, capital B is going to emanate from 2, and capital C is going to emanate from 3. All right. So now I write down the following matrix. In row 1, I take a look at the things that come out of vertex 1, and I put A plus capital A. Those are the 2 things coming out of vertex 1. A goes to 2, so I put a minus A here. Capital A goes to 3, so I put a minus capital A here. I write down the whole matrix, and then you see what the general idea is, and we'll give more examples in a minute. But here we are. So on the diagonal, I list all the arcs going out of of 1, 2, or 3. But in a position ij where I and j are unequal, I put the negative of arc that goes from I to j. Now, interesting thing about this this matrix. By the way, this graph is G. This matrix is called C of G, capital C of G, and traditionally combinatorialists call it the Laplacian matrix of a directed graph, not because Laplace ever saw this matrix in his life, or maybe not any matrix in his life, but because he worked on some differential equations that suggested to somebody some theories that eventually suggested to somebody this matrix, and so it's called the Laplacian matrix. Now, let's take a look at the well, the determinant of this matrix is 0. That's pretty obvious because every row sums to 0. So the determinant has to be, the sum of the 3 columns is 0. So the determinant of a matrix is 0 if there's linear dependence between the columns, but or rows or anything. But if we look instead at the cofactors of the matrix, which means that you throw out any one row and any one column, and you write down the determinant of the rest, then you get something interesting. And so here I show you the example. Take the determinant of b plus b minus b minus cap c and c plus c. Okay, so now I'm not going to use high power matrix theory in this talk, but I am going to use determinants. If determinants scare you, too bad, but just enjoy the jokes. I'm not going to use high power determinant theory either. So the determinant of a 2 by 2 matrix, that's b, this minus this. So bc plus little b big C plus big B little c plus big B big C, that's this times this, and now I subtract the product of these guys, and so that's minus little b big C. And so these are canceling, and I get 3 terms left over. And now let's relate them to the arcs over here. Little b is the thing going from 2 down to 3, and little c is the thing going from going from 3 to 1. Big B was the thing going this way, and little c was this one again. Right, and then big B and big C are this. Now, can anybody figure out what's special about these combinations of arcs? Take a look at the one that canceled, by the way, the little b and big C. Notice what happened there. Those formed a loop. Okay, so somehow when you get one of the things that happens when you expand the determinant of this thing, wherever you have a loop, it seems to cancel out. Okay, so these are called the oriented trees that go to vertex 1. Okay, spanning trees. So an oriented spanning tree of a directed graph is with a certain root, says you take any vertex other than that root, and there's one thing going out of that vertex. So from 2 you have to have one thing coming out, exactly 1. From 3 you have to have one thing coming out, exactly 1. You follow these, and eventually they take you to the other vertex, which is the root. So this doesn't look that much like a tree. Well, I could draw it like this and so on, but that's the idea of an oriented tree. All of the everything has a parent, and you go to the parent, and then to the parent, to the grandparent, and so on, until you finally get to the root, which doesn't have any successor. So that's the idea of an oriented spanning tree. Now, in general, this is what the matrix tree theorem tells you. That is, if you write down this matrix, you take some directed graph, and you if you want to, you can give labels to the to the arcs, and you could write this thing down, and then you throw out everything in row I and column I, and you take the determinant of what's left. And that gives you all of the oriented spanning trees of that graph. Well, now let's take another example. This time I'll have 4 vertices, but I'm not going to have I'm not going to give all the possible edges. So I'll go from 1 to 2 and call that A. I'll go from 3 to 2 and call that B. I didn't choose these labels in any particular way. 2 to 4, I'll call that E. What is C? C is going to go from 3 to 4, and D is going to go from 4 to 3. And F is going to go from 4 to 1. That's enough. Okay, so now let's find the Laplacian matrix of this guy. So from 1, the only thing coming out of 1 goes to 2, right? So I write an A here, and minus A, 0, 0. Out of 2, what do you call, somebody call it out? What?
Oh,
0.
0.
E.
0.
0 minus E. Very good. Okay, now how about the next row?
B plus, no, sorry.
0.
0.
Minus B.
Minus B, B plus C.
B plus C.
Minus C.
Minus C. All right. And now, so okay, you get the idea of Laplacian, and now you might wonder. I told you what happens if I strike out all rows. I mean row I and column I. But what if I strike out row I and column J for something else? Well, then you get a minor of this matrix, and you can work it out. And here's what it looks like. So on the diagonal, you get these. We'll check them. You get the oriented. You get the oriented spanning trees of that directed graph. You see what's happening everywhere else. It's a checkerboard pattern. You got minus, you get plus, minus, plus, minus, minus, plus, minus, plus. So it's like a checkerboard. So everything in the first row is the same, except that alternating signs in the second row, third row, and so on. On the diagonal, you get the thing I told you about. So that's what happens if you happen to, to take your Laplacian and evaluate any one of the any one of the determinants. And so, for example, here from 3, it looked like there's only one way, one directed spanning tree, oriented spanning tree that goes to 3 in here, right? Because from 1, the only place to go is to 2, and from 2, the only place to go is to 4. So if I've taken 1 to 2 and 2 to 4, and now I've got to get to 3 somehow. So 4, I can't send 4 back to 1 because that would get me a loop. So 4 has to go to 3, and so that's the only solution. E 4 to 3 is D. So ADE is the only solution, and that's what we had on the diagonal there. On the other hand, you can work it out. I'll write it out so if you want to check it at your leisure. BEF plus CEF are the ones that lead to A. The ones that lead to B are ABD plus ABF plus ACF. There's 3 ways to get to 2. And down here we have ABE plus ACE. I want to mention a famous unsolved problem. And if anybody wants to solve this one, I might even look at it and sign your thesis. But you have to hurry because I'm going to work on something else before long. But the unsolved problem is this. Take any directed graph and any vertex in the graph and figure out how to list all of the directed spanning trees in such a way that to get from one to the next, you're only taking out one arc and putting in one other arc. For example, BEF, CEF, well, you change B to C. All right, ABD, ABF, change D to F, right? ABF, ACF, change B to C, right? But ABD doesn't go directly to ACF. So no, two oriented spanning trees are next to each other if they have all but one arc in common. And the question is it always possible to go through all of those oriented spanning trees in a Hamiltonian path, in something that's next to each other at every step, and you hit them all, okay? It's a great problem. Nope, obviously nobody knows of any examples where you can't do it. But nobody's been able to figure out a systematic proof that you always can do it. All right, now, of course, I didn't have to form this matrix by writing down these letters here and calculating the determinants. So if it's a real big graph, that's a lot of algebra and cancellation and everything. It might take a long time. But instead, I could replace all of these guys by 1. And then I have 1, minus 1, 0, 0, 0, 1, 0, minus 1, so on. Minus 1, 2, minus 1, minus 1, 0, minus 1, 2, right? And then I would get 2, 3, 1, 2 on the diagonal, and that would tell me just how many there are. It doesn't tell me what they are, but it tells me how many there are, right? Because everything evaluates to the sum of the thing. So here we got a good way to count how many there are. And this could be a big matrix, but it's pretty easy to evaluate determinants. That's an efficient solved thing. Now, let me harp a little bit more about this matrix, though, and that is, let's find its characteristic polynomial. Now, every matrix has a characteristic polynomial, which is defined to be equal to chi of x, or characteristic polynomial of x. And I define it the way I learned it, although Mathematica does it backwards. X times the identity matrix minus the matrix which we're trying to take the characteristic polynomial of. So, for example, C of G. The characteristic polynomial of C of G is this, and it turns out if you take this matrix and you work out its characteristic polynomial. So you calculate the determinant here, and keep track of powers of x. There's 5 people standing in the back, and I encourage you to actually come up in front because it's more comfortable and it makes me more comfortable, and and you might, if you want to get one of these free books at the end, you're closer. So, yeah, thanks. So here's what it turns out to be. You can evaluate it, and you get x fourth. That's easy. That's on the diagonal. And then so in other words, I have x. It's the determinant of this matrix x minus a 0 0, x minus e 0 e, and so on. X minus b minus c. You get the idea here. So I take the determinant, 4 by 4 determinant of that, and here I get x minus x cubed times a plus b plus c plus d plus e plus f, and then plus x squared. I'll write it down in a minute. Minus x times abd plus abf plus ace, and so on. Now, see if anybody can figure out what are the things that I'm writing down here at the bottom. Okay. You said spanning trees? And why do you say that? Because what happened? What's the yeah? I might as well put the matrix X here. You'll see what's happening. F x minus d minus f, and this is 0 d here. Okay, so if I'm going to get a term with one x in it, that means that I pick one of the x's on the diagonal, and the coefficient, and then the way determinants work, then the coefficient of that x is going to be the determinant of everything else. And so if I do that for each, for this x, this x, this x, and this x, I get here. It's the sum of all of these guys that I had on the diagonal there. So that's so this is the set of all the directed spanning trees for all possible roots. Some of them had root 1, some of them had root 2, some had root 3, some had root 4. In fact, it's 2 plus 3 plus 1 plus 2, so there's eight of these oriented spanning trees. But it's 3 of them have 2 as the root. But can anybody figure out? Oh, by the way, what's this coefficient here? X cubed. That's just a list of all the edges, right? Okay, but now what's this? What's this thing in the middle here? What's the coefficient of x squared? Excuse me? Something with 2 edges. That's good. They certainly all have 2 edges, and now it's not every possible combination of 2 edges though, because if you notice, there's 6 edges here, and there are 15 possible combinations of 6 edges taken 2 at a time, but there's only 12. 1, 2, 3, 4, 5, 6, 7, 8, and 11, 12. Yeah, some of these aren't listed here. Without loops, that's part of it. Yeah, but take a look and somebody tell me why BC is not in this list.
Could we see the graph?
Yeah.
Could we see the graph again?
Didn't you remember the graph? Yeah, okay, there you go.
BC is not just a path. Connected.
What's wrong with BC?
It's not connected in that definition. It's not a directed path.
It's not a directed path. Yeah, B has 2 things coming out of it.
It's not a tree.
So what we got to do is we got to choose 2 vertices and something coming out, and not make any loops. That's known as an oriented forest. An oriented forest is like an oriented tree, but it's got more than one tree. So this is the way to take to make all oriented forests with 2 arcs out of this graph. And in general, this is what's going to happen in the characteristic polynomial that you get out of any Laplacian. The coefficient of x is going to be all of the oriented forests that are actually trees. the coefficient x squared are the ones that are going to have oriented forests that have that are made out of 2 trees, and so on, 3 trees, 4 trees. You can't have 4 trees on you can. I mean, the empty graph is an oriented forest that had on 4 trees, but you can't have the case of 0 trees in an oriented forest. So that's why this is always a multiple of x here. All right. So that's a property of the matrix tree theorem that's not very often mentioned. That everybody usually only talks about the thing about taking the minor of this matrix, but the characteristic polynomial tells you more too. All right. Now let's start. Let's start using some interesting graphs, but I'll show you a bunch more. And one of the first that you might try is on 4. Well, let's go to 4 elements. Let's stay with 4 elements for a while. But now I've been talking about directed graphs. And really, undirected graphs probably arise in most applications, or at least most things are known about undirected graphs. And as time goes on, we're learning more and more about that the directed graphs have a lot of great properties too. But usually, you have an undirected graph, which is really, in most cases, the same as having a directed graph, but every edge in an ordinary graph is actually an arc going this way and an arc going the other way. So we write it only once, but really it stands for 2 arcs. So each edge is 2 arcs. Okay, so what's the Laplacian? Here I'm only going to count how many things go out, and I'm not going to give names to these arcs. So how many things are touch 1? So it's like this, right? 1 goes to 2, not to 3, and it goes to 4. 2 goes to 1. Actually, it's symmetrical. In an undirected graph, this matrix is always symmetrical about the diagonal. Okay, so 2 goes to 1 and to 3, not to 4. And then 3 goes to 4, and coming back here, and 4. So this is the matrix. This particular graph, it's a square, but it has two main names. One is that you could call it the two-dimensional cube, and P2 square P2 is a nice way to write it. We'll generalize that later, but it's also called the 4 cycle, C4. And this is what it has as its Laplacian matrix, and the characteristic polynomial is x to the 4th minus 8x cubed plus 20x squared minus 16x. And the reason is that if we want to look at this directed wise, let me show you the spanning trees that are rooted at 1. Okay, what I have to do is I have to put an arrow in each one, and so that everything except 1 has an arrow coming out of it, and 1 is the root. All right. Now, these are the oriented spanning trees of this graph that are rooted at 1. Now, if I but I first drew it I first drew it unrooted, unoriented. And the nice thing about this this graph is I suppose I just take a spanning tree of an undirected graph, and so that just means I choose edges. I choose n-1 edges that connect up the graph. It means that there's no cycles, and this is the definition of a free tree in general, a spanning tree. A graph with n vertices, you choose n-1 edges in such a way that it's all connected up, or in such a way there's no cycles. So those two conditions are equivalent to each other, and those are the spanning trees of the graph, and they are extremely important in solving electrical circuits and all kinds of stuff. Now, after I've drawn it, though, if I decide that one of the vertices is going to be the root, then I just draw arrows so that everything shows the way to get to the destination. All right. So, for example, if I wanted 2 to be the root, and this will work for any spanning tree of a graph. Now, if I say put arrows on here so that it becomes a directed spanning tree, what do you do? Well, from every vertex other than 2, there's a unique way to get to 2, and so you just say which way you go to it, right? So for example, I would do this because I have, wherever you are, there's one way to get to 2, and that defines the arrow. So this connects up the undirected graph idea to the directed graph theory, and the undirected graph is simpler. Because the matrix is a symmetrical matrix, and so a lot more things are true about symmetrical matrices. Okay, now, but you'll notice then that every spanning tree occurs n times if there's n vertices, 1 for each root. Okay, so that's why you got 16 here. There are 4 spanning trees of this graph, but each one occurs 4 times. Okay, so the coefficient of x is always n times the total number of spanning trees, and that's a crucial thing because one of the things we want to learn here is count how many spanning trees are there in a graph, and it's always the coefficient of x divided by n. Now, by the way, what about the forests? The spanning forest, and there are the following spanning forests. I'm going to draw just a few of them, but you'll see what I mean in a minute. Here, arrow going this way and this way. I have an arrow going this way and this way, and an arrow going this way and down. But you can't have arrows going away and to the right and away down. That's not allowed. Every vertex has to have either one successor or no successor. And 2 of the vertices are roots. So here I get up, up, or up, down, or down, up, or down, down. So that I'm trying to explain why there's 20 here. Let's see. There are four times. There are 4 cases like this. Yeah. So there's 4 times 3 is 12, and there are 2 cases like this. These 2 guys and these 2 guys, and so that's 4 times 2. So the 12 and 8 is 20. So that's why there are 20 guys here. Okay. So anyway, that's the characteristic polynomial. And by the way, the characteristic polynomial factors x minus 2, x minus 2, x minus 4. Okay. So that's the two-dimensional cube. a graph. Like that. And do one more four vertex graph before we're done. That's K4. That's the complete graph on 4. Everything is connected to everything else, and the matrix looks like this. It's got 3s. Everybody has 3 things, and -1 everywhere else. And if you want to look at the characteristic polynomial, it turns out to be x to the 4th minus 12x cubed plus 48x squared minus 64x, which factors into x times x minus 4, x minus 4, x minus 4. Believe me. All right, so that's, you can work it out. Just write down the matrix, calculate the determinant, and so on. I'm going to give you a couple more examples, and then we're going to see why this all fits together and makes really beautiful patterns, beautiful theory. And I think the best one to go to next is the three-dimensional cube, which is what a cube really is. So notation is P2 square P2 square P2. And it looks like this, sort of. I don't know. There are people who draw much better cubes than I, but this will be good enough for today. So let's call this 1, 2, 3, 4, 5, 6, 7, 8, for example. And the matrix looks like this. Every vertex has degree 3. And 1 is connected to 2, 4, and 5. And so I work it out here. So you just get the idea that 2 is connected here. This one goes to here. This one will go here. They seem to be connected to the guys on their left and right. So it's like that. -1, -1, -1, -1, -1. We'll put a -1 over here, and then over here this got to be symmetrical. So this is O -1. Okay, so this is a 8 by 8 matrix. I'm not going to have courage to do anything bigger today, but we're going to have theory so that so that all of a sudden we don't have to write down all this stuff. We can actually calculate it without a lot of extra work. Okay, here's the matrix then, and what is it? What do we get as a typical spanning tree, for example? So that means choose 7 edges that connect everything up, and one of the typical ones might be, say, this. And, okay, for example, 1, 2, 3, 4, 5, 6, 7. Okay, so you might say, how many spanning trees are there of this cube? And that's I write down the characteristic polynomial in factored form. It's x times x minus 2, x minus 2, x minus 2, x minus 4, x minus 4, x minus 4. This is like high school. Everything factors. You get a polynomial. Okay, now, so if you work it out, this is equal to x to the 8th, minus something or other, and so on, and then you get a minus 3072x at the end here. So how many spanning trees are there? What?
Divide by 8.
Divide by 8. Yeah, 3072 over 8 is 384. So it turns out there are 384 spanning trees of the of the cube. All right. A few quick graphs on five vertices so that you can see that this theory doesn't only work for the graphs you've seen before. This is a kind of a weird graph. Just happens to be there. But before I tell you this, I better tell you, explain the title of my talk now. The talk was called Spanning Trees and Aspects. And I've got to tell you now that the aspects of the cube are 0, 2, 2, 2, 4, 4, 4, and 6. Now, every graph on n vertices has n aspects, and they are the roots of the characteristic polynomial of the Laplacian. Okay, so now if it's an undirected graph, this matrix is symmetric matrix, and it's well known that the characteristic polynomial of a symmetric matrix always has real roots and always has non-negative real roots. It's a semi-definite matrix because it's diagonally dominant. There's always these n roots of the characteristic polynomial, and I'm calling them the aspects. Now the reason is that I've seen them arise in many problems, and I decided that there ought to be a special name for these guys. Some people say they're the Laplacian eigenvalues of the graph. That's a big mouthful. It's too long to say Laplacian eigenvalues 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 syllables for such an important concept, right? So I got to have a short name for them. So I decided I got out Rosé's thesaurus about 10 years ago, and I'm saying what's the best, what's a word that hasn't been taken yet about graphs that's still pretty short and memorable, and that would convey the essence of what these 8 numbers are for an 8-vertex graph. And my answer was I was going to call them the quanta of the graph. So I said these were the quanta of this graph. All right. Well, then I happened to be on an outing with Michael Dube, who's one of the greatest experts of this whole theory of the characteristic values of graphs, and he also has written some books about tech. That's how come I met him. But we were on this excursion, and I'm saying, oh, Michael, let's call them quanta, and he didn't like it. So then we spent the rest of the day brainstorming, and we both liked aspects. All right. And so we wrote some letters back and forth later on, and we still came to the conclusion we do like aspects. Now, of course, we can't push this. I mean, I'm not like I'm not going to go to Geneva and talk some international committee into making nomenclature. I wish I could do that sometime, because they come up with a lot of really stupid things. I mean, why is a yottabyte bigger than a zettabyte, right? I mean, you think they, at least when they get up to the end of the thing, they would go in alphabetical order. So, so these standards, it might never happen that the whole world switches over to aspects, but it's so much better than anything out there. I'm hoping that by making this lecture now, and if all you guys tell a friend, 2 friends, and each of the two friends, then in 5 years everybody will know what the aspects of a graph are. But one thing I can be sure is, whatever they're called, rose by any other name, as you'll see soon, aspects are terrific. Okay, so now here's a typical graph on 5 vertices, and what the aspects of it are. It has 5 aspects, and it turns out to be 0, 1, 1, 3, and 5. I usually list them in increasing order, but that's, they're always non-negative for an undirected graph. Here's C5, the 5 cycle. Its aspects turn out to be, 0 is always one of the aspects, by the way. That's obvious, because it's always a multiple of x. There's never a constant term on this thing that's determined as 0. Put x equals 0, you always get 0. So the aspects here are 0, 3 minus golden ratio, 3 minus golden ratio, 2 plus golden ratio, and 2 plus golden ratio. Oh, sorry, 2 plus golden ratio. So golden ratio, you know, so 1.6. So this is about 1.4. So you know, they aren't always integers. You can if they were always integers, that would be really beautiful. That would be really great. But that just doesn't work that way. Here's another sort of random graph on 5 vertices, just to give you an example of what happened. And there's an atlas of graphs where all the small graphs it lists all their aspects. But it usually gives them numerically rather than in symbols. Okay, so here you are. Now, main thing is, now we define what aspects are. Let's calculate with them. Let's see all kind of things that they do. And one of the things we already know is that the number of spanning trees. Okay, the aspects are 0, or alpha 0 is 0, and then the other ones up to n minus 1. The number of spanning trees is class alpha 1, alpha 2, alpha n minus 1 divided by n. Okay, that's the coefficient of x. Because it's because we have x times x minus alpha 1 times x minus alpha n minus 1. That's the characteristic polynomial. Okay, so one of the things about aspects is that they tell you how many spanning trees there are. Now, suppose I know the aspects of a graph. I'd like to now figure out the aspects of the complement of the graph. The complement of a graph is defined. You say that two edges are adjacent in the complement if they're not, if and only if they're not adjacent in the graph itself. Two different edges, and so, for example, take this strange graph I had here. Call this G, and C of G was 2 minus 1 minus 1 0 0 2 4 1 1. You see that vertex 3 here is connected to to everything else. 1 is connected to 2 and 3, and 4 is connected to 3, and 5 is connected to 3. That's it. Okay. Now, what about C of G bar? This is 2 0 0 minus 1. You see, wherever I have a 0 here, I change that to a minus 1. So I get a 0 minus 1 there, and I get zeros here, and I get minus 1 minus 1 minus 1 0 minus 1. With me, I'm just complementing. Where I have a 0, it's non-zero. So then I have to add up here. I got 2. Here I get 0. Here I get 3. Oops, I put a little typo there. Okay, so here's the C of G bar, right? Now, I think I have time to. I think I have time to prove one result, so that you get the idea of how these matrix schemes are proved. So anyway, if you look at C plus C bar, this add these to this, what do you get? It's 4 minus 1 minus 1 minus 1 minus 1. You get 4s on the diagonal, and you get minus 1 everywhere else. Okay, so this is C of G plus C of G bar, and it's equal to C of K5, or the complete graph, and it's equal in this case to 5I minus J, where I is the identity matrix, and J is the matrix of all ones. Okay, so I is equal to the matrix 1, 1, 1, 1, 1, and zeros everywhere else. And J is the matrix 1, everything, all ones. Right? So I take 5i minus j, I get 4 on the diagonal, and I get minus 1 everywhere else. Okay? So now what I'm going to do is I'm going to tell you if you know how to figure out the aspects of G bar, if you know the aspects of G. And it requires a little calculation, but I'm going to do it. And for those of you who understand matrices, determinants, you'll see. Otherwise, it won't take long. So I say, let C be any matrix whose rows sum to 0. The row sum, add up every row and you get 0. Then I'm going to write down a formula for the determinant of xi plus yj minus zc, where x, y, and z are arbitrary numbers. I'm going to give you a nice formula for this determinant. So what's this? What's the? I'm going to work it in the case n equals 3, and this will be completely general so that you'll understand what would happen if n was equal to 1 billion. So this is the matrix. When n equals 3, the matrix looks like this: x plus y minus z c11, y minus z c12, y minus z c13. Okay, the diagonal entries are always x plus y minus z times c sub I. And the off diagonal ones are z. This will be z c21, z c31, so on. Okay, z c 1, 2, 3. So here's the matrix, and I want to calculate the determinant. Okay, I want to simplify it, so I add columns 2 and 3 to column 1. That gives me well, these columns 2 and 3 don't change, but I'm going to add them to column 1. Sorry, C322. X plus y minus z. Okay, so add it to column 1. What happens? I get x plus 3y, and then minus z times c11 plus c12 plus c13, but that's 0. I said that the rows sum to 0. So I get x plus 3y everywhere in that first column. I added columns 2 and 3 to column 1. Okay, so now I'm going to factor that out, x plus 3y. Actually, I'm going to factor out x plus 3y over x, and that's going to, and then I'm going to get x here, and I'm going to have the same, and then I'm going to have y minus z. I'll keep these. So first of all, I factor out x minus 3y over x, and so I get x here instead. And now I'm going to subtract y over x times this from these two, and I'm going to get z minus z c12, x minus z c22, and minus z c32 here, and I'm going to get minus z c13, minus z c23, and x minus z 33. I got rid of the y's here by subtracting y over x times the first column from the second column. Then I subtracted y over x times. That doesn't change the value of the determinant. So now I got rid of the y's have disappeared from this equation, so we're making some progress. Now I subtract. Now I go back and I subtract these two from the first one before I added them. So now I subtract column 2 from 1, column 3 from 1, and what I get here is x minus z c1 actually, and minus z c21 minus z c31, and these other two columns stay the same. And so what I have proved by this derivation is the following. I wound up with x plus ny over x times the determinant of xi minus zc. all this derivation. I got rid of, I started with this guy, and I wound up with a matrix that has x's on the diagonal and minus z c there. Okay. So and so this is also equal to x plus ny over times z to the n times the determinant of x over z I minus c, for example. All right. Now this little theorem is going to tell me then how to calculate the aspects of the complement of a graph. The reason is we have observed that C of G bar is equal to Ni minus J minus C of G. So the determinant of the characteristic polynomial of this thing is the determinant of the xi minus C of G bar, which is the determinant of x minus n times I plus j plus C of G. Now I plug into my general formula for evaluating all of determinants of this form, and I know how to do it, and you can check it out. What do you get? It turns out that this turns out to be equal to x times x minus n plus alpha 1 through x minus n plus alpha n minus 1. And so therefore the aspects of G bar of G equals 0, alpha 1, alpha n minus 1 imply aspects of G bar are 0, n minus alpha n minus 1, n minus alpha 1. Just I'm writing them in increasing order again. For example, take C5. Remember, C5 is this graph 1, 2, 3, 4, 5, and its aspects were 0, 2. I'm sorry, 3 minus phi, 3 minus phi, 2 plus phi, and 2 plus phi. These were the aspects of the 5 cycle. What about C5? What are the aspects of the complement? So C5 bar. The aspects are 5 minus this is 3. It turned out the same thing. And the reason is that the 5 cycle is also its complement. The complement of C5 is 1, 3, 5, 2, 4. I mean, it's just it turns out that this is a self-complementary graph, and so naturally its aspects are symmetrical in that way. Remember, we had the aspects of the complete graph. K4, I had that way back here. Remember, they were 0, 4, 4, and 4. Okay, now what's the complement of the complete graph? It's the empty graph, no edges, right? Now, what are the aspects of the empty graph? 0, 0, 0, 0, 0, right? It all checks out. This is the complement of the empty graph. Okay, now, but I do want to show you now how we march along and develop the theory of aspects more, and so I want to talk about the direct sum of graphs, which is a very trivial way to get one graph from another, of G and H. So authors don't agree on notation, but this one is beginning to win, and I have Baba's help on this. G plus H, the direct sum, just means take G and take H and put them next to each other, and you got the direct sum of graphs. So, for example, if G is C5 and H is equal to our two-dimensional cube, or C4, then G direct sum H is the following graph on 9 vertices. Looks like this. Okay, direct sum of graph. Pretty easy. But what are the aspects of the direct sum of the graph? Okay, well, take a look at the Laplacian. So we got, I got the 5 cycle here, sorry. And zeros here, and then H, the other vertices, the other 4 vertices make a 4 cycle, so that's this guy. So what you do is you just, the C of, in other words, C of G of the direct sum of H is the direct sum of C of G and C of H. This is called the direct sum of 2 matrices. If you take one matrix and then you put the other one up and you put zeros in between. Okay, so the aspects then are so G has aspects are 0, alpha 1, alpha. Well, you can call it alpha, up to alpha m minus 1. And H aspects are beta 0 through beta sub n minus 1. The aspects of G direct sum H are alpha 0, alpha 1, alpha n, m minus 1, beta 0. You just take the union of the two. If you want to sort them into order, you can. So that's real easy. And so what are the aspects of this graph on 9 vertices? Well, 0, 0, 3 minus phi, 3 minus phi, 2, 2, 2 plus phi, 2 plus phi, and 4. Because I got 0, 2, 2, and 4 from H, and I got, the others from G. So these are the aspects. Notice there's 2 zeros now, right? The number of zeros is the number of connected components of a graph. So every connected graph has just 1 0, but the empty graph was all zeros, and the number of zeros, the number of times the aspect of 0 is that's the number of connected components of a graph. Okay, now the interesting thing though, this was a trivial calculation, but now we can take the complement of a direct sum. The complement of this graph, you see, what does that look like? Well, the complement of, I could put a 1, 2, 3, 4, 5 on it. So I have 1, I'll redraw it here. 1, 2, 3, 4, 5, and 6, 7, 8, 9. Now I take the complement of this, and so that's 1, 3, 5, 2, 4. This is the complement of the cycle, and the complement of that is 6, 8, and 7, 9, and then all the edges between these two. So 1 is connected to 6, 7, 8, and 9. 2 is connected to 6, 7, 8, and 9. All that's the idea, and we call this this is G bar joined to H bar. So another thing you can do to 2 graphs is, instead of taking the direct sum, you can take their join, which says take G and take H, and then everything that goes between them. And so what it turns out is that the aspects, so if I complement, to get the join of 2 graphs, I can complement G, complement H, and take the complement, I take the direct sum and complement that. And so I can apply my theorem that I know about taking direct sums and complements, and I get the formula for the aspects of the join of 2 graphs, not the join of the and the aspects are the following: 0, m plus n, m plus beta 1 through m plus beta n minus 1, and n plus alpha 1 through n plus alpha n minus 1. So if I know the aspects of G and aspects of H, I have a simple way to calculate the aspects of their join, which means I've put all the connecting things between them. A quick example of that, earlier I showed you this particular graph, and I said that its aspects were 0, 1, 1, 3, 5. Now, in fact, there's a simple calculation that you could do this without evaluating any determinants, because this graph is equal to K1 joined with K2 direct sum K2 bar. Namely, you take the one vertex graph in the middle here, and you join it to the graph K2, which is this times this, and K2 bar, which are these two isolated vertices. Okay, so now you just apply the formula that I had before, and you can figure out the aspects. You know, the aspects of K2 are 0 and 2. Aspects of K2 bar are 0 and 0. So that's the aspects of this guy. And the aspects of K1 is just 0. And so what I get is 0, then m plus n is 5. And then I have m plus beta 1. So I'm going to get the 0, 1, 1, 3. Comes right out of that calculation. So you can work that out afterward. Okay, now we're running a little short on time, so I want to get to one more beautiful thing, and that is what about G square H? So that's another nice way to combine two graphs. This is their direct sum, direct product. It's got different names, but and it's so important an operation that it has many different notations. But this is the only notation that hasn't been co-opted to something else. Well, all the other notations turn out to be, some people use well, they've written 10 papers and they use different notation in each paper. But this one is winning now. So let me explain what this operation is on two graphs. And so if I take G is C5 and H is C4 again, what you do is you make copies of G, like in this case 4 copies of G. So I have 20 vertices in all, if there were 5 vertices in G and 4 in H, and then I join corresponding things in the different ones if they were neighbors in H. So these will go like this, and there will be five things coming over here, and 5 things coming down here, and 5 things coming down here, but nothing going across here because those aren't adjacent in H. So that's the idea of G direct sum, or what is it called? I don't remember. I forgot the name of this darn thing. Yeah. So if you get this for Christmas, you look at page Cartesian product. There we go. Cartesian product of 2 vertices. So here's the the direct sum. We got the join, got the Cartesian product. There's a bunch of other nice products. Here's the direct product or the conjunction of 2 things. There's a strong product. There's an odd product. There's a lexicographic product. And these are all associative operations and all arise in lots of applications. And if you turn to exercise 105, it turns out that there are nice ways to calculate the aspects of all of these things if you know the aspects of G and H, or in this case it's G prime and G double prime. And also, if you want to get the line graph of a graph, that's another thing. So all of these calculations on aspects work. I'm talking about part D here, the Cartesian product of 2 graphs, and we're short of time, but the form for the Laplacian matrix is actually not too hard to understand, and we saw an example of it when I drew this here. I had sort of, this looks like P2 Cartesian product with P2 here, and this is here. So then essentially, you take C of G and write it on the diagonal, and then you add minus ones according to. I'm sorry. There would be only twos there. Then you take the C of H, but the actual formula is I cross C of H plus C of G cross I. This is an m-dimensional identity. This is n-dimensional. This is called the Kronecker product or Cartesian product of matrices, and so this is what C of G star H is, and Kronecker product of matrices has lots of nice determinant formulas that make it easy to calculate it. So what it turns out are the aspects of G and H are the sum, alpha 0 plus beta 0, alpha 0 plus beta 1, and so on. It's all the alpha I plus beta j are the aspects of the Cartesian product of two graphs. Therefore, we can see why I got the aspects here 0, 2, 2, 2, 2, 4, 4, 4, 6, because I started out with P2. It's just a same as K2. It's the aspects are 0 and 2. This is P2, then P2 star P2. I take 0 plus 0, 0 plus 2, 2 plus 0, 2 plus 2, and then to get to the cube in 3 dimensions, I take 0 plus 0, 2 plus 0 plus 2, and so on. I add 0 and then I add 2 to everything. So I get this right now. We'll do one more, and then you'll see what's happening. This is the 4-dimensional. Here's your hypercube. This graph on 16 vertices. What are its aspects? How many twos are and again, I got 4 twos, 6 4s, 4 6s, and 1 8. So it's going to turn out just you just take all of these guys and then add 2 to them all, also, and this is what you get. So in general, you see what's happening here. This is 4 guys. This is 6 guys. This is 4 guys. This is the 1 here, and this is 1. This is binomial coefficient. So this is 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Now, and so how many spanning trees does this hypercube have? Well, 2 to the 4th times 4 to the 6th times 6 to the 4th times 8 to the 1 divided by 16. Okay, but this, in general, we're getting 2 to the, a d-dimensional hypercube. So d choose 1, 4 d choose 2, and so on till we get finally to 2d to the d choose d divided by 2 to the d. Spanning trees of a d-dimensional cube. All right. Well, let's just because these are the aspects of the n-dimensional hypercube, and so I can take out a factor of 2 here. There's how many? The sum of all these binomial coefficients is 2 to the d minus 1. So it's 2 to the d minus 1 times 1 to the d1. 2 to the d choose 2 up to d to the d choose d. And then I divide by 2 to the d, so I subtract d. So here's a glorious formula for the number of spanning trees of a d-dimensional cube, and that is what I promised to teach you today. I mean, in the abstract of this talk. All right. Well, so I'm about ready to wrap up. But coming back to the beginning, you remember we were talking about directed graphs, not just undirected graphs. This whole theory of aspects applies also to directed graphs, but hardly anybody has talked about it because they were worried about it because the aspects of a directed graph are complex numbers in general. They aren't real. And I don't know, that seems scary or something. I don't know. But all of these things still work. You can define the Cartesian product of directed graphs, the complement of directed graphs, the arc directed graph, these other forms of products that I talked about. They work on directed graphs too, and even more. Besides a join, you can have a directed join where you have G arrow H, which says you take a directed graph G and a directed graph H, and then you also have a line going from every vertex of G to every vertex of H. And you can calculate the aspects of all these things. And therefore you can calculate the number of directed, the oriented spanning trees. The formula, when you divide by n, you're not getting the it's a little different in the directed case because as we saw, sometimes there's more spanning trees that have one as a root than have two as a root. But when you divide by n, what you're getting is the average number of spanning trees, averaged over all possible roots. But all the formulas then go through, and the aspects of an oriented cycle turn out to be 0 and 1 minus omega. 1 minus omega squared through 1 minus omega to the n minus 1, the oriented cycle, where omega is nth root of unity, complex number. And so then you can consider oriented cycles with Cartesian products, and you get lots and lots of very nice results about exactly how many oriented spanning trees they have and so on. Okay, I'm done. Any questions?
Do the aspects help? Do the aspects help determine the graph uniquely in certain ways?
Yeah, that's a natural question. Can different graphs have the same aspects? The answer is yes, they can. But it's a pretty good way for sorting. So if so a lot of times you can determine you can determine that graphs are not isomorphic because they don't have the same aspect. But there are but it was a conjecture for a while, and then but then somebody found, I think, a graph from 13 vertices that that the two of them had the same aspects, and it's and these coincidences aren't so rare after you get to larger and larger graphs. But that's certainly a natural question. How much does it characterize it? But then, what happens if you take a graph and you add one edge to it? How do aspects change? So there's this kind of nice geometry here because of known theorems about eigenvalues of matrices. Yeah.
You could do the whole. You could construct a Laplacian matrix for a simplicial complex and not just a graph. Is there some similar interpretation of the things we're counting?
I never thought of that. That would be that's a really cool idea. In other words, try to consider hypergraphs instead of okay. I bet there is. Maybe next Christmas we'll talk about it. Yeah. Yeah. Okay, so Merry Christmas to all, and remember there's all these freebies sitting out here. Okay.